Welcome to another video lesson. Today's video starts chapter 6, a new chapter, a new textbook even. We're starting volume 2 as well, and this marks the beginning of the next 3 chapters really. Actually, if you really want to call it, the next 5 chapters kind of build on top of each other. So it's really important to go step by step through the concepts that we're going to be learning in chapter 6 because they will come up again in future chapters. This unit also starts talking about more of our algebra topic that we learn about in 6th grade. It's one of my favorite things to teach, so I'm really excited to start this chapter with you. We're going to be talking first about powers and exponents, so this should be a review. And we're going to fill in our table of contents. You were given 2 note sheets. It's going to actually span across 3 different pages. So I've written out 64 and 65 where my pages are, is going to be the powers and exponents. That's the yellow sheet. You're just going to snip that in half and put it across 2 pages. I actually had to go on the right-hand side and then on the back. And then the blue one you can just trim down. That's going to be dealing with some square roots. So here's some visuals before we get to our notes for you. Talking about patterns. We're going to be dealing with the pattern of repeated multiplication. So when you have a string of numbers, you can write it in a shorter version, and that's called exponential form. So you have the number that you are multiplying multiple times, and then that's called the base, and then the exponent is the number of times you're going to be multiplying that factor, that number. So 4 with an exponent of 2, it also is a power. So you could read this 4 to the 2nd power, or a special way to read powers of 2 is the word square. So we could also say that this is 4 squared. If I flip the exponent and the base number around, it's a lot different because now we're taking the number 2 and we're repeating that a lot of times with multiplication. So 2 times 2 times 2 times 2. How many times am I going to multiply this? This exponent tells us we're going to multiply the base 4 times. It's also could be called the index, but I'm going to mainly refer to it as the exponent, or to the 4th power is the other way that we can read this. So 2 to the 4th power. There's no special way to read this other than 2 to the 4th power. So we have the big number, the number being multiplied is the base. The little guy hanging up on the right-hand side is the exponent. So very simply put, this is the shorthand way, 6 to the 3rd power. And then it means that you're going to multiply this base number by itself 3 times. This is a special one as well, just like the squared exponent. You can call this 6 to the 3rd power, or you could say 6 cubed. So those are the only 2, the exponent 2 and the exponent 3, that have 2 special names to say it. And let's deal with our notes now. So I want you to actually underline the 5, actually draw an arrow and label it the base, and then do the same thing for the 2, and that is the exponent, or the power. So again, the base is the factor, the number that's multiplied multiple times. The exponent tells you the number of times to multiply it, and it's a shortcut for repeated multiplication. So that 5 is going to be repeated in multiplication only 2 times. And 5 times 5, if we were finding the value, would be 25. Now, I just want us to write out, we could say this 5 to the 2nd power. That's one way to read numbers in exponential form, but this is the one special guy that's actually another way to read it is 5 squared. If you're paying attention, make sure you put a star on the upper left-hand corner of your note sheet at this point, and we'll then continue on. So let's explore the pattern that we're seeing. all throughout chapter 6, we're going to be talking about patterns that we notice with numbers. And this is the start of it. If we just have one number and it's not being multiplied by anything, we can show that in exponential form as 2 to the first power. So anything raised to the power of 1 is just itself. It's not multiplied by anything except times 1. Similarly, 2 times 2, there are 2 2's. So we have 2 as the base, and the exponent is 2. 2 squared, we could read that, or 2 to the second power. Then that's going to be a 4. Make sure you put a box around that 4 as the value. Now we have 3 2's. Because the base is 2, the big number is a 2, and then the exponent tells us how many 2's are being strung along and multiplied together. And if we were to multiply and find the value of this, it would be 2 times 2, which is 4. And then we have to take that 4, multiply it again by 2, and then we get 8. Make sure you box that 8 as well. The last one I have here is still the base of 2, but there's 4 of them now, so the exponent is 4, and we read it 2 to the 4th power. Going back up here, we would read that 2 to the 3rd power. Remember, this guy is a special one as well with the power of 3. We can also read that 2 cubed. Now, to solve the value of 2 to the 4th power, we would have to multiply 2 times 2, which is 4, and then take that 4, multiply it again, which is 8. 4 times 2 is 8. Then we have an 8, we have to multiply that by 2, which is 16. So I want you to notice, and you boxed all of these answers. I'm going to actually put this there. So if you notice these answers, 16, 8, 4, and 2, you could go backwards and find a pattern. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. So if we wanted to find out what 2 to the 0 power is, we could finish this pattern by dividing 2 by 2, and we would get 1. This is a special thing that happens. Any number raised to a power of 0 ends up being 1. This is a special phenomenon that happens, and you can see that pattern. You can do that with any number that you choose to increase its exponent by. You can see that pattern, and it will always go back to whatever that base is, raised to the 0 power will be 1. It's kind of a cool thing that happens. So moving on, we're going to first practice just writing each product using an exponent. So we have a string of numbers. We want to use the shortcut exponential notation way to write this string of multiplying repeated numbers. And it happens to be that our base, our number that is being repeated, is 6. And then you have to count how many times it is being multiplied. That is our exponent. For example 2, we have the 4 that is being repeated. That's our big base. How many times are we multiplying it by itself? 3. At this point, we don't need to solve the value. We just want to practice writing the exponential notation. If you could put your age at the bottom right-hand corner, then we'll move on to the second part of this lesson. Now that we've practiced writing repeated multiplication in exponential form, we're going to go the other way. So now we are given the exponential form, and we have to stretch it out and write it as a product of the same factor, and then actually multiply them all out to find its value. So the value, finding its value, is actually telling us to go ahead and solve what is that really as one number. So let's work through these. Then you have 5 to try on your own. So 4 squared, or 4 to the second power, is a string of multiplication with 4. I'm going to show the multiplication with a dot. Remember, multiplication could be a dot, could be an X, could be that little asterisk, and we're going to learn a new way to show multiplication as well coming up soon. So since we only have an exponent of 2, we only need to multiply 4 times 4, and that will equal 16. Notice, for example, 4 and 5, it's not a whole number. We have a decimal and then we have a fraction. So I'm going to walk you through these, and then you'll have a chance to practice in the U-Try. So this is the base. Even though it's a decimal, 1.5 or 1 5/10 is going to be the number that's repeated over and over and over again. Exponent tells us how many times that is going to be multiplied. And now this is going back all the way to chapter 3. We are multiplying decimals again. When we're multiplying decimals, we're going to take 2 of them and multiply those together. Go ahead and do that. So once I've multiplied, I have 225. We have to put the decimal in. So since there's 1, 2 decimal places, I have 1, 2 decimal places, so I have 2.25. But we're not done because we have to multiply this by another 1.5. After we do this, we'll have our final answer. So go ahead and multiply this. Check with me once you're done. After you do all the multiplication, you should have a 3, 3, a 7, and a 5. But we have to place our decimal point. So we're going to count 1, 2 decimal places, and then a third with that second factor. So we have to put the decimal place right in between those 3's. So we have our final answer of 3 and 375 thousandths. Last one is a fraction. So that fraction, 1/2, is our base, what we are going to repeat by multiplying it 3 times. Now, multiplying fractions is not new either. We're going to multiply the numerators across, then multiply the denominators across. 1 times 1 is 1, times 1 is 1, 2 times 2 is 4, 4 times 2 is 8. So you will see whole numbers, decimals, and fractions. You have 5 U-Tries that review exactly what we went over. I'd like you to try them on your own, so go ahead and do that. So the first 2 were like our first 2 examples. We had to just write it with an exponent. We have 4 7s being multiplied together, so that is 7 to the 4th power. If you think you're going to forget how to read this, I would jot this down as well. If you are good with reading powers and exponential notation, you don't have to write it down. Example 2 should have been a base of 9 and an exponent of 7, and that's read 9 to the 7th power. On the bottom 3 examples, 3, 4, and 5, you should have had 4 3's. I actually do this little V thing and I write down the product of 2 numbers. And so 3 times 3 is 9. These 2, the last 2, is also 9. So 9 times 9 is 81. If you wanted to do 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, that's okay too. And then example 4, we have, again, the 3's being multiplied, but now they're in the denominator. So we have 3 times 3 is 9, and 9 times 3 is 27, so we have an answer of 1/27. The last one, we only had to multiply a decimal twice. So I did that over here. I got a 4, 4, and 1. The decimal has to go in between the 2 4's because there are 2 decimal places in our factors when I add them up. So we get 4 and 41/100ths. So before we go on to that blue page, make sure on the bottom of the yellow you write down the last meal that you ate before watching this video. And now we're going to go on to perfect squares and square roots. On this blue note sheet, you have the definition of a perfect square, and I have some examples with pictures to show us what I'm talking about. A perfect square is a number that has 2 identical factors. So if you look over here, we have 2 times 2, and if we were to show that with dots, we could draw a perfect square with a side of 2 all the way around, and then we could do the same with a box that's 3 by 3, 4 by 4, 5 by 5, and 6 by 6. So these are what's called perfect squares, and it could go all the way. I stopped at 9 times 9, and that's really a reason why we can call 2 to the second power 2 squared, because if we were to show that with a picture, it would make a perfect square. And these have a special notation that we can use to go back and forth between the answer of what is 2 squared and 2 squared, and that is to take a square root of a perfect square number. And that symbol I'd like you to draw in that parenthesis on your note sheet, and you have a picture. Instead of the dots, you have the number 64 representing 64 dots, and you could have 8 dots on the bottom and then 8 dots on the side, and then total it would be 64 on the inside. This right here is one of the sides of the square. I'd like you to make it a little bit darker. Thinking about a plant, the roots are on the bottom of a tree or a plant. Think of the square root of a number as being one of the sides of the square. And I like to think of it as the bottom because it reminds me of where the roots are. So here are the roots of this square root. And so the square root of a perfect square number is 8. And it's the factor that is the same on both sides. So we see the perfect square, the 64 number, inside this symbol, and then the answer is the 1 of the same factor. So because 8 times 8 is 64, the square root of 64 is 8, and 8 squared would equal 64. A final little note. Remember I told you that when something is raised to the third power, it's special as well because we could call that 3 cubed or 8 cubed. A perfect cube is the 3D version of a perfect square, and it's a number that has 3 identical factors. So it's like 3 times 3 times 3. My example is 2 times 2 times 2. So if you had a cube, one of the sides would be a 2, the other side would be a 2, and same with the third side. So this is a perfect cube because all of the sides are the same, and we can represent it with 3 identical numbers being multiplied together. We've just learned that this is 2 to the third power, or 2 cubed, and 8 is a perfect cube. We can also show this as a cube root, and that would be 2. So I just have a few more pictures to show you about this cubed root pattern that we see, and then we'll be done. If you want to think of your favorite shape and write that on the bottom of the blue sheet, that would be great as well. So here you see all of the patterns of 1 to the third power, 2 to the third power, and so when we actually string out 2 times 2 times 2, it is 8. If we take the cubed root of 8, we would get 2. It's just talking about one of those sides that are the same of that cube. So you can see that raising something to the third power, we could go the opposite way and take the cubed root. This is a little bit more advanced. We're not going to worry about cubed roots tomorrow in class. I just wanted to give you that background in case you ever see that in the future. Look forward to seeing you tomorrow. We will be practicing just powers and exponents and writing them different ways. See you then.